Uh, Thank you. So, good morning, everybody. Thank you, Pablo, for the introduction to the basis of the foundation of the high-field compact tokamaks. So I will be talking about the fusion-to-grid strategy that we are leading at the Plasma Science and Fusion Technology Laboratory in the University of Seville towards the most compact fusion power plant. I am one of these optimistic guys that think this can happen within the next decade, and we only need to work in parallel and enable the key technologies that are missing now to have it. And the fusion to grid and the smart tokamak is just one of these steps. We are now here trying to have the best of a conventional tokamak and the best of a spherical tokamak to have the most compact fusion power plant possible. Now, how we are doing that, we are combining three technologies that are very well known in the community. We are putting spherical tokamaks that are more compact and efficient, high temperature superconductors, I don't have to explain why, Pablo did it fantastically, negative triangularity, that is a special plasma shape that gives you minimum plasma wall interaction and maximum reactor lifetime. And we combine everything in a reactor that can actually produce the energy you need. Caveat here, warning, there is no magic. You need a meter of shielding for the coils. So there is a minimum size that you can have. No? In the end, it's a neutron wall load that is defining the size of your machine. So if we go to spherical tokamaks, so spherical tokamaks offer an attractive path to a fusion power plant. We know that conventional tokamaks are the best established power plant design, have large surfaces to distribute the power exhaust, but has also cons that we know, large capital cost, investment, and time scales. On the contrary, spherical tokamaks shows that they're more compact, and indeed they can actually have plasma pressures that are just about 40% larger than in conventional tokamaks. And this is rooted in the basic equation. So actually, a spherical tokamak is more stable than a conventional tokamak. Now, if you look at the fusion performance for conventional tokamaks on the top and spherical tokamaks on the bottom, and Pablo showed this picture before, you can look that you have also the energy gain, the different capital Q energy gain figures, and you have here as a reference ITER with the parameters of ITER. And if you go down at the same magnetic field, spherical tokamak would be just something, a major radius of 2 point something. So in terms of volume, you would be something like 20 times smaller. Think of what is that? 20 times smaller if you think of it capital cost and the time you need to build it. No? Of course, there are challenges. And challenges that you cannot increase the power density as much as you want. You face problems. You face engineering limits, physical limits. And the main one that you face with the spherical tokamaks are extreme power exhaust. And you can see here where the hot plasma hit the wall. And this is the diverter problem that Gianfranco was mentioning. But you also have a scarce room in the center stack. How? Now you need a meter of shielding for the coils. How do you do that in a spherical tokamak? Oh, we have a problem. You need to breathe tritium. Oh, how do you do that? You don't have the center stack room to have your breathing blankets. And here is where negative triangularity comes to save us. So negative triangularity here emerges as a potential game changer for spherical tokamak. I think it's not only for spherical tokamak, it's also for conventional tokamak, but in particular for spherical tokamaks. Here, you have in negative triangularity, and this is something that was shown already in the 80s, but has been revisited now at TCV, at D3D, at JET, in DT plasmas. We have enhanced core plasma performance, low fluctuations here. In the figure you have in the front, negative triangularity plasma in the smart tokamak that we just put into operation in Seville. And in the back, you have the same tokamak with a positive triangularity plasma. Higher fluctuation levels, and super important, a larger diverter weighted area where the power exhaust is distributed. So naturally, your diverter is located at larger radii, distributing this enormous power exhaust in a huge Not huge, but in a lot larger area. So that problem is solved here. But from the physics point of view, it's fantastic. But from the engineering point of view, it's amazing. So you have room to have a sandglass solenoid. You have suddenly, with negative triangularity, with the shape that your plasma is giving you, you have room to have a massive solenoid, the solenoid of a conventional tokamak, to drive your plasma current, to sustain your pulse. Now, you also have enough room for the shielding of your coils. And you also have enough room for the breathing blankets in the center stack, where a spherical tokamak usually has important challenges and problems. No? Now, to prove this, we built in Seville the smart tokamak, no? The small aspect ratio tokamak. That is just proof of concept for high field negative triangularity spherical tokamak path to the most compact fusion power plant. The missions, compact spherical tokamak with high fields, and we are using HTS coils. The tokamak was built with copper coils, and we are now, thanks to the grant that we got from the national agencies, CERETI, that Belen is here, to exchange coils. We are going to be starting with colloidal field coils and diverter coils and putting HTS coils, insulated and non-insulated. We're using negative triangularity and fusion temperatures. No? The machine, as you can see here, is a reality. We installed the center stack last year in January, and in October we got the first plasma. So we built the machine in something like 2 years, and it's been and with very limited resources, as you can imagine. No? So it's a way to do it. You just need to work in parallel. No? But smart is just the first step in this fusion to grid strategy. No? The final goal is to have the most compact fusion power plant. Combine these technologies in a unique global integrated solution, as it was also mentioned before. We need an integrated viable solution. No? And this is coming with the project that we call eSmart, negative triangularity spherical tokamak for most compact fusion power plant design. And here we're doing all the calculations, including engineering constraints, to have a fusion power plant with producing 500 megawatts, a capital Q of something like 25. Now, important, look at the capital Q is P fusion divided by the power you need to run the machine. An important point here is the external heating power. Reduce that. That's an important goal that we have in the system. Reduce that to the maximum. No? And how to do that? So we have an important solenoid. And we rely also on important booster current fraction. So you reduce that, your capital Q naturally increases. No? Now, with this big solenoid, you have a pulse length that is something like more than 2 hours. You have a neutron wall load and the shielding that can tolerate something like about 1-2 megawatts per square meter. Tritium-bearing ratio that we have simulated also with conservative breathing blanket designs using MCMP or Serpent, state-of-the-art codes, that is greater than 1.15. But we also have a diverter load that is a lot lower than you could have in ITER, just because the diverter is placed at large radii. No? So if you look again at where are we? It's nice to have just a figure, but now where are we actually if we put the engineering constraints? Here we are. No? So we have the fusion performance, radius, major radius, magnetic field, and now you have here in dashed lines, you have the most important engineering constraints. Now obviously, as you advance with the engineering design, you will have to add additional engineering constraints. But I'm putting here the current density in your toroidal field coils. This current density is a super conservative one that is including also the stainless steel structures that you need. No? And this is having here something like, it's less than 100 amps per square millimeter. If you are aware of HTS, this is a super conservative number. No? You have also here, you can see also the 70 centimeter shielding, and we are well above that. So we have the emitter shielding for the inner wall. You have also the magnetic field, maximum magnetic field, and in the end, where you have here the point where you have the current driven by your solenoid, 50%, boom, this is my minimum. And this is the machine with 2.8 meters in major radius, capable of producing this 500 megawatt. No? This has been patented, and there is no publication now because we were waiting for the patent to come out. Now, we are here, we would like to be here, and we believe we can do it within the next decade, but there is an important gap in between, and it was already mentioned. So we need to bridge this gap. We need to enable key technologies. Breathing blankets is super important. And for that, there is a fantastic idea, and that is unfortunately already 30 years old. It's a volumetric neutron source. It was suggested 30 years ago, and it's being revisited now because we need it. We have HTS, we can have super important breakthroughs, but if we don't have breathing blankets, we cannot do that. The uncertainties are huge, no? So let's do it. And here we have also a machine, and it's actually, the size is similar to what was proposed already 30 years ago, 1 meter. 1 meter major radius. You have a capital Q greater than 5, so alpha heating. You test also alpha heating, but it's also a test bed for breathing blankets and other integrated key fusion power plant technologies. And with this last slide, thank you very much for your attention.